Good morning, good afternoon, everybody, and welcome to another monthly ARA Webinar Wednesday. Today's program, Knowledge-Guided Machine Learning for Geotechnical Resilience. So we're going to learn about two new topics, knowledge-guided learning, as well as kind of address some issues I'm sure you have related to resilience. I'm Jerry DiMaggio, by the way. I'm your moderator for today's program, as I often am. I'll be using a little bit, or we'll be using a little bit different format for today's program. We'll have a lead presenter who I'll introduce momentarily, but we'll also present it more in the form of a podcast. So myself, Jerry DiMaggio, and our speaker who I'll introduce momentarily will be sharing information with you. Now I'd like to introduce my good friend, colleague, and our presenter for today, Dr. Ahmad Alhasan. Ahmad is a principal engineer and a team leader at Applied Research Associates. He works in our Research and Technology Deployment Group. His specialty areas are geotechnical asset management, infrastructure management, pavement performance evaluation and management, pavement surface characterization and safety impacts, statistical and data-driven analysis, and multi-attribute decision-making under uncertainty conditions. I don't think he ever sleeps, and I work with him on a regular basis. So with that, let me turn the program to my friend, Ahmad.
All right, thank you, Jerry. And again, as you mentioned, we'll be talking about resiliency today and geomaterials or geotechnical assets resilience and a little bit of machine learning. Originally, I was planning to talk more about some final findings for some work that we have been doing, but I think we'll have more of a general discussion, and then we'll talk about some of the applications for machine learning. So here's the outline of the presentation. We'll start with the resiliency and then move on to the three other topics. The two in the middle will be discussed in one sitting.
So, Ahmad, thank you for being here with us and sharing this information. As we all know, many of us, including myself, resiliency has become an increasingly important topic. It's become today's buzzword, so to speak. Everyone knows what a buzzword means. And there's now a desire to incorporate resiliency into multiple aspects of really all types of infrastructure, including geotechnical engineering and transportation asset management. So let me begin by asking you a few questions, if you can help our audience out. First of all, it'd be helpful, how do you define resiliency? Recently, it's become a household word, and I myself find that many people have different definitions. Second question is, why should we consider and apply resiliency in our geotechnical practice? And the third question is there some degree of urgency in the way of a need for this? Where does it fit in overall geotechnical practice? Does it fit into design, or is it in the service life aspect of geotechnical assets, or is it pervasive throughout?
So these are all really good questions and very critical to help us with this discussion. I will do my best to address most of them, but the order may be different than the questions were asked, because I'd like to start, first of all, with the role of resiliency, why we're doing resiliency, and why would this be important. So, first of all, the terminology comes from biosciences, actually, talking about the ability of a system or a biosystem to recover and respond to certain events, extreme events. But for our applications, it came into transportation and civil engineering in general. And the increase in interest in applying resiliency concepts or evaluations and take care of the resiliency of our systems actually comes from several sources. One of them would be the increased number of extreme events that is related to climate change. And it is evident that there is an increased number of extreme events. And when we talk about extreme events, that includes floods, freeze and thaw cycles, and many other extreme events. Some of them did not actually increase in number, but also what happened over the time that the number of people and the assets that are present in, let's call it an extreme event prone zones, have increased over time. So since, for example, 2020, globally, the population living in flood zones have increased by 20 to 24% actually in 10 years, which is 10 times more than what our models have predicted previously. So there is an evidence that there is increased number of events, and more importantly, there are increased number of assets and users that live in these areas that have more extreme events. One other thing, as you can see, there's the flood, typical flood picture, but I want to debunk that. It's not only about floods. There's also the freeze and thaw cycles and extreme cold weather, for example. These cycles are, even though there's global warming, the cycles are being more extreme now. So overall, you will have more meltdown, but that would lead sometimes into cycles of deep freeze, more severe, and all of that would affect deterioration of the assets. And one thing before we move on about resiliency, it's not about total failure. So as you can see here in the photo, we're talking about the collision basically that happened previously in a project. And I think, Jerry, you were involved in some of these projects, but one of the main things in here when we talk about resiliency, we're talking about recovery. So these assets are not supposed to fail totally, or if they do suffer from some localized failures, they can be fixed. They will stay operational. It's not total failure. And that's actually the difference between extreme event designs and resiliency. Now that we have a good reason to think about resiliency, let's talk a little bit about definitions. So there are two definitions that I picked. There are many definitions out there, again, as I mentioned, and they are open to interpretation in some cases. The first one is the simple definition that appeared in different locations. It's the ability of a transportation system to absorb, that's the main thing, to absorb disruptive events gracefully, so it doesn't fail, and then it restores its pre-disruption level of service. And that word is important. Does it go back to full level of service? Typically, it doesn't. Now, in the bipartisan infrastructure law, resiliency is defined as the ability to anticipate, prepare for, or adapt to conditions, or withstand, respond to, or recover rapidly from disruptions. This is a long definition, but it's all-inclusive in some sense. And that includes the ability to resist hazards or withstand the impacts of weather events and natural disasters. So we're talking about both weather events and natural disasters. And in my opinion, we should even go beyond that to a general definition of disruptive events. But this also, limiting the discussion to natural hazards and weather events, is also good in terms of tying resiliency with sustainability, and there's always that tying there. Or to reduce the magnitude or duration of impacts of a disruptive weather event or natural disaster on a project. One thing to highlight here, it's talking about a single project. So there are different definitions, as I mentioned, and you can find them all over the place. But the main point that I want to drive out of this is, first of all, it's not total failure. Secondly, it's open to interpretations. And there are different ways to think about resiliency at this stage. So let's talk more about quantitative concepts. So this is not the full equations, and I'm not going to dive much deeper into all the equations and analytical tools that can be developed in there. But let's put things into a frame of quantitative response. So the plot here to the left shows you the performance on the y-axis. And when we talk about performance, it could be, for example, the capacity to move or transport traffic, the capacity to withstand loads. So there are different measures of performance, and that is important to keep in mind. But we will plot performance versus time. And as that asset lives in there, typically this is the normal assumptions with geotechnical engineering, even though we all know it's not always true that things will just keep going at the same pace. However, internally we know that there is some cumulative damage, but let's talk about the simple case. There will be some fluctuation in your performance, it doesn't matter, and then all of a sudden you face a disruptive event that will start deteriorating the performance for a while until you reach the lowest performance level possible at T1, and then it recovers. As you can see, I left a gap in there because typically these assets do not fully recover always. Sometimes they do, sometimes they don't. Now, the main distinguisher, whether they go back to the full recovery or not, is your performance measure. So if we're talking, for example, about opening to traffic, your performance can go back to 100%. You will pass the same traffic levels. However, if we're talking about long-term performance and deterioration, for example, end of service life and all of these aspects, then most probably it won't recover back to 100%. Now, some of the components that go into the definition of resiliency is robustness. So robustness in here, as you can see, is what is the capacity of this to go and absorb a certain level and stay above some level of performance. Time to recovery, that relates to rapidity of the system. How much does it take you to go back to normal conditions? And that is a function of multiple aspects, including plans and so on. Resourcefulness, do you have the resources to recover? And redundancy of your system. And that plays a major role when we talk about network level assessment. It is important that we talk about these individual components. Now, we eventually would like to have a simpler number that we can, for example, summarize with. And that's a very plausible approach, that we want a single number. However, we shouldn't totally cover the components and just ignore them over time as we do the analysis. So let's talk now a little bit more about geotechnical projects. Where does resiliency assessment, design, or the word resiliency comes in? So it starts with actually site investigation. So knowing more about your site, knowing what is in there and the challenges that you have, the data that you have, and the material properties should be assessed in a sense that it would feed into resiliency. Resilience-based design, again, it's not only extreme event design the traditional way. This is targeting recovery over time. So resilience-based designs as well. And there are some geotechnical asset management aspects when we talk about resilience assessment of in-service assets, your maintenance practices to improve resiliency, and planning and project selection overall. So, Jerry, you've been involved in multiple projects. Where do you think, have you seen resiliency being really taken into consideration?
I think it's spoken about more frequently on a daily basis than it had been. And like many of these topics, it takes a while to get a foothold and to demonstrate, first of all, how to do it. And second of all, what's the return on investment and how to apply it. So I think the key message in this slide, number 10, is it's pervasive through the entire process of the life of a feature, whether it's a geotechnical feature or some form of a physical infrastructure feature.
That's interesting. And I think one thing also that it shouldn't be a great burden. I mean, once we can show the return on investment, it shouldn't be a burden on the agency or the designer to perform such analysis or such procedures, because eventually it would save costs down the road, but that should be also done in a smart way, because you may end up spending too much money on planning for resilience and a network. Awesome. So now also that goes into, again, as I mentioned, the network level assessment. At the network level, we're more focused on keeping the network fully functional, so we're not talking about the individual assets necessarily. And also, network level assessment is critical for cost-effective solutions. When we have plans, long-term or long-range plans, sometimes called, we better account for resiliency, and that obviously plays into asset management, transportation asset management, and geotechnical asset management, one of my favorite topics that I typically talk about.
So before we move on to the next topic, I think what you just said is pretty insightful to me. It's interesting that resiliency includes, first of all, the multiple components. I believe that was slide number 8, and they need to be evaluated separately. But moreover, as you introduced in slide 11, is the trade-off or the consideration of looking at an individual asset level as well as a network level and the trade-offs between the two. So for that aspect of it, how should an owner or a designer representing an owner go about assessing resiliency? Do we start at the network level and move down to the asset level, or do we do that reverse?
That's a very important aspect. Now, based on what I have seen and what we have developed recently, and we both actually worked on this, I would say the answer would be somewhere in between. So there's no clear line saying that you should target network level all the way or asset level all the way. It should be somewhere in between. So here's a general framework for resilience assessment that we have recently developed together, actually. Jerry and myself, we worked on it. And it starts by defining the assets of a network, and that would take us into risk-based data collection, and then defining disruptive events, and that would require some kind of risk and vulnerability assessment for the assets that you have. Then we talk about analysis of asset system response, and that's, I think, one of the crucial parts nowadays. People are more aware of the previous two, but this one is a little bit tricky. Quantifying resiliency, again, resilience measures and measurements, there are different definitions. So selecting only a couple measurements is sometimes challenging. And then eventually improvement strategies. So this is not only an assessment of giving a number, but also includes the planning and decision-making under uncertainty for future improvements. And since we're talking a lot about uncertainty, I think I should touch base on risk assessment and risk management for just a couple seconds here. This is a crash course in 2 minutes. So what is risk? Risk is the effect of uncertainty on objectives. This is a short definition. There are also many definitions out there, but this one I like because it's short. It's straight to the point. You're not sure about the future, and then you want to see how would that affect your plans or objectives. And the effects could be positive or negative, and we're typically concerned about the negative ones. Uncertainties, the main thing, they are all in the future. If it happened already, you should know better, unless you don't have enough measurements. But the future, we're talking about uncertainties in the futures. And the objectives, this is also important to know what you want out of this asset. So sometimes your objectives can affect your planning goals as well. And since we mentioned uncertainty, and this is a major part of resiliency, uncertainty and the definition of uncertainty, surprisingly, it's not as straightforward as everyone would expect. Uncertainty is not only the segments in your distribution. Sometimes you may have some unknown unknowns, that's what they call them. So we have things that we had no clue about, and these typically are referred to by black swan events. And for some reason, people try to associate risks and risk events to animals for some reason. And the black swan, the story goes that back in the days in Europe, they haven't seen black swans. Most swans were, or all swans in Europe were white. And then when explorers went outside Europe, they were surprised that there were black swans out there. And people were talking about black swans as imaginary animals or creatures, but in reality, they are all over the place outside Europe. In some locations. So that's where the name comes from. And then there's also the gray rhino, which is basically things that you know about, but you overlook. You know that it's coming your way, and you just have been either didn't have resources to address or didn't know how to address them. You know that it will happen, but you're not sure how to respond to it. And also, two other things, and maybe I should have started with these, is it's sometimes can be due to the inability to describe or quantify events. So some of these events are too complex, and we'll see some of these actually as we go through here. Things are not uncertain in the sense that they are totally random, but they are too complicated and the interactions are complicated to be addressed properly. So there's always that uncertainty due to lack of knowledge, and let me say it that way. Now that we know what risk is about, this is obviously a very I would say, representation of risk management and risk assessment, but we don't want to spend too much time on it and divert from our topic, risk-based data collection. What we do with risk-based data collection is try to go out and have a staged procedure. You collect data, for example, at the network level because you cannot really go and investigate every single geotechnical asset that you have. And currently, many states, or if not almost all of them, they don't know exactly where all their geotechnical assets are. I know that when I say that several times at conferences, the people that know that from agencies, they were not surprised at all. Actually, they are asking for that information, but some other people were surprised. How could that be? So they designed them at some stage, but they are sitting on a shelf, limited accessibility to them. You know that there is a wall when you pass by it, but you don't have it in a database that you can go out and revisit the same wall and compile data. So that's what I mean by they don't know where some of these assets are. So you go out, have a general inventory, and then start doing some kind of a staged data collection. If the asset is at higher risk, and the way you assess risk in here, it's not modeling the total risk of one geotechnical asset and go into details, but it's rather a more generic approach of what are the risks if I don't really measure or go out and assess these features. Sometimes the answer would be, yes, this feature is in a good shape, but we don't have any information about its history. So we need to go out and start collecting data over the years to observe the trends. Otherwise, you would not know where this is going. So this is one aspect, or sometimes it looks bad and it's deteriorating very fast, so you should have a closer look at it. And then you start going out and do more cycles and investigations. So the question with risk-based data collection, what are the risks associated if we don't go out and measure? And according to that response, you can come up with a tiered approach of less extensive data collection, mediocre data collection, and then detailed data collection for assets that you need to keep an eye on. The other aspect, again, we talked about it, and the loop in there, about the resiliency assessment framework was the risk and vulnerability assessment. And that is important to understand the events that you have. What are the events that you expect? Where do you see them happening? Can you quantify them? Can you quantify their consequences? And Jerry, let me turn back to you at this stage. So you've done a lot of risk assessment and risk management work with geotechnical projects, geotechnical assets. What would you say is the status currently regarding of the implementation of risk management? And do people typically do quantitative, qualitative, or a mixture of both?
Well, that could be a webinar by itself, but an elevator answer to that would be, first of all, risk management has been a best practice, to use another buzzword, since the 1970s. In different segments of the infrastructure community, it's been embraced. Our good friends at the Corps of Engineers have done this on a regular basis, in part due to the terrible situation that was caused by Katrina and Rita. Other segments of the community, in particular the geotechnical community for highways, have done maybe not so good a job as they could in terms of looking at risk from a design and construction point of view From the aspect of looking at risk and vulnerability from an asset management point of view, the stigma which is slowly being overcome by the geotechnical community is geotechnical assets have a defined life. You know, what's the life of an embankment or slope? We've never, up until recently, have had to answer those questions. Again, this could be a webinar topic all by its lonesome.
Oh yeah, I agree. This is so vast in terms of topic. By the way, that's a coincidence. Vast is also the vulnerability assessment scoring tool by US DOT. So there are some resources out there, but again, going back to this topic, it is a big topic and it deserves a more detailed discussion. But again, we're trying to cover that. But I appreciate your comment regarding the, the specific life of these geotechnical assets, and that would take us into basically the cumulative damage concept. So when we talk about asset or system responses, you have an extreme event. What you want to do is to see what is the sequence of events. And here I'm giving just a simple example of an embankment. My drawings are not as pretty as they should be, but I'm an engineer. I'm maybe good with blueprints, but not really fancy sketches. So there's an embankment in there. You have a pavement section, and then you have culverts. A culvert that would drain any possible, not any, but flood events. And then that embankment also is supported by a retaining wall in there due to some issues with the right-of-way and all of that. So let's take an extreme event, for example, a flood. Again, this is the typical scenario, but it could be applied to other concepts in there. Your water level will start rising. Your culvert should provide enough drainage, but what if the culvert is not in a good condition and it's not draining as it's supposed to drain? And then your water level will start rising up all the way to the top. Now, if it overtops the pavement and wash it away, that's total failure. So we're not talking about resiliency at that stage. It's just extreme event condition, failure under extreme event. But if we're talking about resiliency, that level of water would impact basically the capacity of the embankment, and you will start seeing some deformations in there. And these deformations can also happen to the retaining wall. So the retaining wall, if it's not good enough, it's not supportive enough, this segment especially, if the retaining wall moves, leaves a gap in there, you will have even more and more basically deformations out there. The performance of the pavement during the flood event, it cannot hold many heavy loads. After the flood event, it may go back, but it won't go back to 100% serviceability levels because you have deformations now. So cumulative damage, that's a concept that we don't typically, we know about it. There are even some studies out there, but we don't really typically consider it in the design for geotechnical assets. Pavements, folks, and I'm half pavements person, half a geotech. We typically consider cumulative, this is how we design pavements. We assume that cumulative damage and we try to model it over time and give you our designs to resist that cumulative damage. And with that, let's move on to basically how we quantify resilience. So quantifying resilience, again, I won't be as extensive because it's still open. Different assets have different ways to define them, but generally speaking, you can have a resilience index as shown here in the first bullet point. This is a general definition. It tries to capture basically the opposite of this area under. So the area under this curve is actually a bad thing. The larger this is, it's less resilient. So what you're trying to see is what is the opposite of that, and that's why we have the integral in here of the function, which is basically the area under that curve. Rapidness, that would refer to the time it takes to go back to normal conditions or the best you can go back to. So it doesn't need to be 100%, but the best you can go to. Now, a more realistic approach is to look at the deterioration as we talked about it right now, cumulative damage. Geotechnical assets do deteriorate over time, and we all know that. But typically with the designs, we don't really account for it. We account for design lives, and these are different than service life. But again, this is a long discussion that would be required for a different webinar by itself. So what you're trying to do in here is to look at what is the acceptable performance that can be achieved And that acceptable level, basically, let's say that, and your robustness, going back to robustness, and we talked about that earlier, is how good or how many times, or what is the time that you maintain it above that acceptable condition. So after a disruptive event, you will have that disruption in here. That's a reduction in your serviceability at acceptable level, and also you will have that reduction in remaining service life. So that's in a nutshell, a very quick overview of quantitative resiliency assessment. And that would take us to the improvement plans. And there are different ways to improve robustness. Resiliency. You can talk about robustness. You can talk about network level redundancy, maintenance effectiveness, that you need that information to really derive your plans, and then also look at some kind of return and risk trade-offs when you do your improvement plans. Now, mentioning that, Jerry, you've worked with all agencies and all state agencies. What is the typical practice, you think, in terms of improvement plans? Not necessarily resiliency, because I know not everybody is accounting for that, but generally speaking, when we have a collection of assets.
I think it's historically it's been a worse first examination. I don't think that's necessarily bad. I think where we're headed is more sophisticated examination of improvement plans. And to use another cliche, we've been using a lot of them. The return on investment is quite critical. We look at some things like structural monitoring that have been around for quite a while, and not to suggest that the work that's been done is poor, but the stigma to making it mainstream acceptance is a demonstration of the return on investment and how to model that, the so-called improvement plan connection that you have here. So Ahmad, while we're on this topic, so everything that you've presented up to now, it makes perfect sense, I think, to myself as well as hopefully to everybody in the audience today. However, it's going to be, I'm assuming, fairly challenging for owners and engineers beginning to consider this topic of overall resiliency and implement it in their practice. But the other title, or part of the title that we started with, is how does this all apply to knowledge-guided machine learning? Can you speak to us about that and tie it to resiliency?
Well, I'm glad you reminded me of that. I was diving into resiliency and the fundamentals of that. But let's talk about machine learning now. So let me start with the general definition of machine learning. Again, this is not the ultimate definition by any chance or by any stretch, but machine learning is a branch of artificial intelligence. As many of you already 100% know that, and it aims at observing trends from data and learn, and that's cumulative learning, on how to maximize or develop a machinery that is capable of making strong predictions. So the main purpose of machine learning, and I'm not trying to put it in a one box, and we'll talk about boxes in a second, but the main goal is making good predictions. And for a reason, I use the word machinery in there, because it could be an algorithm and mathematical process. So it's not only about computers per se, it's definitely the application is in computers. There is no doubt in that, but machine learning comes from the fundamental concepts of statistical learning. So if you have enough time, infinite time, you can do it yourself on a piece of paper, or a pile of papers. Actually, you can just run the thing yourself and try to reach answers. So here's a simple, again, oversimplified explanation probably. When we do machine learning, you have target responses that you're trying to predict. So you want to know more about soil shear strength parameters or properties. You know that there are some potential influencers, such as soil chemistry, geology, soil gradation, locations for some reason, and you're not 100% sure why this happens. Some of these we have good models that tie, for example, stress history with some of the properties of the soil, but we don't have a collective model that looks at all of them, and some of these we don't even have good models for. So what you do, you compile observations for responses and inputs that you think that they should affect that. You feed them into your process, and that process doesn't need to know the fundamentals. All what it's trying to do is to maximize the likelihood, and the likelihood is the probability that your model that you're trying to fit meets the data that you have provided. So the likelihood of that model, you fine-tune the parameters, and there's what is called loss functions, and the loss functions basically, these are the functions that minimize the errors. So you try to minimize your loss function, and then you come up with a trained system or machinery that can provide you predictions based on history. So machine learning in general, in the general sense, is awesome with finding trends that humans typically cannot find. Your data can be just super messy, and machine learning can make sense out of it. But the user should be able to know what they want to model, or should actually know what they want to model. So, for example, for our application in resiliency, where machine learning can fit is or develop better performance forecasts of the assets and the network level. So sometimes we don't know. We have a lot of uncertainties when we talk about the future, even though we have observed multiple assets, but we always are surprised how assets change from location to location and under different conditions. You can estimate the capacity over time, how it changes. Again, we talked about cumulative damage. We don't have good models for that. We have some observations, so putting this into machine learning process can give you some insights. Assessing risks, definitely that's a big thing. You know, risk models are very sophisticated, and having closed forms is not easy. It's a big challenge. And then you have also the response that we talked about, you know, how under a certain condition, disruptive event, how your culvert would behave, how the retaining wall would behave, how the entire system would respond. All that interconnection that is really sophisticated to model, you can start thinking about machine learning. And then maintenance effectiveness models. We have a lot of lost data. Can we use that? So let's talk now about the trade-offs between physical models and traditional machine learning. So traditional machine learning is what we typically are used to do with machine learning, statistical learning theory. They have a loss function. The loss function tries to meet the data and the model in the middle. So that's traditional machine learning. And then the physical models are our typical, for example, corrosion models. So let's see here, we have a corrosion situation. We have inputs, environmental conditions, and we have a bunch of nice corrosion models. These are good models. However, they work under controlled environment. So what you do, you get a lot of observations. You try to fine-tune your model, given the outputs that you have observed, and then you can predict service life for an asset. However, we know it's messy. This is not specifically for corrosion, by the way. I'm going to be very clear about this and honest. We're working a separate project actually on corrosion that we're doing some analysis and modeling in there, but this comes from a previous study that we worked on culverts condition. It's messy. It's never really fitting that model in the middle in there, the blue line. So you end up with a lot of uncertainty in your model. And the reason for that you're trying to pile up all the assets under different conditions, under different loading and environmental conditions, and call them the same thing. And that's not true. So what machine learning would do in that case, it would start accounting for other variables that we cannot really do very well with modeling. We can eventually develop models, maybe at some point, but it's too tedious and there are too many variables that we don't want to really develop closed form models for. And the interaction between these sometimes are almost impossible to predict. So feeding this into your machine learning system, and this is again a traditional machine learning, you fit observations for parameters, for example, again, concentrations, weather impacts, how close is it to basically a water body, and all of these aspects, you give it some kind of measurements. It could be some kind of corrosion measurement, I would say. And then you would fit or train the model by minimizing your loss function. So your loss function is trying to develop a model, and that could be a sequence of linear models or a sequence of nonlinear models. That doesn't matter. When we talk about traditional machine learning, what you're trying to do to find the best set of models, regardless whether this is realistic, this really represents the physical activity, it doesn't matter. What it matters is try to get as close as possible to the observed data. So you come up with predictions, but what happens with these traditional models, in many cases you end up when you forecast with these errors. So things are amazing. It's not only good, it's perfect almost. But then when you predict in the future, you know your assets are not machines and they will not always respond the same way. Conditions have changed or you have accelerated deterioration at some point. You will start seeing some differences in there. And that's what led people to think about, basically, the limitations of physical models and machine learning. So there is a limitation when you have machine learning. You need a lot of data. If you don't have data that covers that future forecast from a previous history, you will not do very well. And again, needs a lot of training, needs a lot of maintenance. Physical models or theory-based models, that's what, by the way, when we talk about physical guided or knowledge guided, theory guided, they are all basically referring to the same setup of machine learning algorithms. Now, theory-based only models, which are the physical models that we use to develop, they use very limited amount of data, and they depend a lot on the scientific knowledge, but you don't have enough parameters and variables to model all the conditions out there. So you end up also with bad predictability in there. It's all over the place throughout the model. This one, machine learning, traditional machine learning, it looks amazing until you go outside the boundary of your training data set. Now, theory-guided data science combines both worlds. So the aim of machine-guided or theory-guided, knowledge-guided, physics-guided machine learning is to combine both and take advantage of both. So what we do with knowledge-guided machine learning, you have the observations that we talked about in the typical and traditional machine learning, and also you would have your physical models. You feed some of these inputs to the previous physical models that you need, you know that they need to meet. So there are some boundaries, for example, based on physics and knowledge, that you cannot go beyond these numbers. This is the boundary of it. This is the physical fact that nobody can defy. So you model that, but you capture the uncertainty from the observations. You combine these two, feed them into machine learning algorithm, but here's the trick. It's not only you feed them into the machine learning algorithm, but you also adjust your machine learning algorithm to have additional components for loss function that would capture how far you are from the physical model. So you try to minimize also the distance between your predictions and the physical model that under controlled conditions should be valid. With that, you come up with an amazing knowledge-guided machine learning process and you provide predictions. Now, what are the advantages and beauties of knowledge-guided machine learning? Needs less data since you can also use your models to guide things. So it's some sort of supervised learning in some sense. It can be designed to improve over time, and that comes with, especially when we talk about Bayesian networks and all of that. It allows for physical interpretation. Your models are not black boxes. When I say we will talk about boxes, the traditional machine learning is sometimes referred to as black box, even though it's not the right terminology in my opinion, because some traditional machine learning allow for physical interpretation, but it's very limited compared to knowledge-guided machine learning. It can be generalized. You can go beyond your boundaries because you know that you have the fundamentals of that model, and the machine learning aspect of it is just trying to capture that uncertainty that you could not capture with the physical model. It's physically consistent. It would not give you crazy, inconsistent findings. And all of a sudden, in the traditional machine learning, your models can flip if your training data set or your model is overfitting at some point. It can flip on you and give you something that is inconsistent, totally awkward numbers that don't make sense. So you can avoid that with knowledge-guided machine learning. I know that was brief. We are working currently on a project to implement some of these. We have some amazing team members here at the area that are knowledgeable about machine learning. Myself, I've done during my PhD, my minor was in statistical learning and the application of that for profiling and image processing. Now, looking to the future, where does that knowledge-guided machine learning comes in? Sharing data from different locations. You will have big data. There is a tendency now to talk about global databases, nationwide database, where you can also utilize all of that to improve your predictions, because sometimes geotechnical investigations are expensive. Use it to interpret and improve the interpretation of geotechnical properties, as we talked, and organize the data. Improve risk analysis, 100% that's important. Capture the uncertainty in these sophisticated models with multiple interactions. And finally, improve the predictions and improvement plans. These are some of the main features, I think, of machine learning. With that, Jerry, do you have any insights into this aspect?
Well, just quickly here, we talked about the future, and it reflects back to me on the past and the present. The past, in 1973, is when I began my career, and we were still in the heyday of the earthworks business and transportation and highways, and we kept using the same techniques over and over again to repair landslides, but we really didn't have the technical manuals. We didn't really have the design processes and procedures that we now have in place. Certainly, we didn't have the software tools. So the connection of creating those products really were a crude form of machine learning, if you will, because we took all those individual project knowledge and experience and wrapped them into training courses and manuals. So let's look at the present. And probably you mentioned corrosion, and I've worked quite a bit in underground corrosion, and that's a great example of a need for machine learning, where we look at a problem like that, and depending on how you count them, we have somewhere between 12 to 15 variables, but we don't really know how they interact with each other. So we use, because we have to design things today, we use crude models that are based basically on pH and resistivity. We know they don't capture all of the 12 to 15 variables, but that's the best we could do, and that is a great problem to be solved by machine learning.
That's beautiful. I worked a little bit on corrosion, but you know what? I didn't think as much about it, so that probably should be our next thing to work on.
Yeah, we're at the conclusion of the technical program today, and we have received a number of questions, but I'd like to move on with a bit of a commercial about our next programs, if you will. So on this slide, I just want to share, first of all, we have many repeat participants, and thank you all for doing that. We certainly appreciate it. Our mission with these programs is to share our knowledge and our experience with the respective disciplines and communities. So the next three that are coming up on September 27th, remember, ARA Webinar Wednesdays are always on Wednesdays, generally towards the latter part of the month. Matteo Cavalar will be presenting a topic on pavements. Actually, the next three programs are on pavements. Transitioning from manual to automated distress identification for Florida's statewide pavement condition survey. On October 25th, Dr. Brian Moon will present a AL application on pavement crack detection using UAVs. That is an emerging topic as well, in line with the resiliency that we discussed today. And then finally in November, late November, November 29th, Safrul Khan will present evaluation of pavement performance and condition using numerical simulation. And I want to remind everybody, we're embarking very closely on our 5th anniversary of ARA Webinar Wednesdays. We've got our program scheduled now through March of 2024. So watch your emails for updates and visit the Webinar Wednesday webpage, as you see it highlighted on this slide. So with that, let's move to Q&A. and we've got a couple of questions. Time permitting, we'll address as many as we can. If we don't get to your question, by the way, during the available time that's remaining, Ahmad has been gracious and has included on this slide his email address, and please feel free to send him an email, ask a question on the topic that we discussed today. So first question is, now as the era of generative AL is emerging, how do you think it will affect the prediction modeling system? That's a pretty bold statement. Will it augment the current physical and machine learning models, or, long question, forgive me, or still is there a lot of uncertainty regarding generative AL models at large and modeling? So, long questions, I guess.
Yeah,
so
and
between AL and resiliency and our historical practice of physical modeling and knowing the limitations of those.
No, that's an amazing question. I believe that it would definitely improve our predictions. AI applications will definitely take us to the next level. However, one thing that is really important to keep in mind for the future is we don't want, because nowadays with, for example, the new technologies out there that helps you write things down and helps you, I won't mention any specifics, helps you write codes as well. These are awesome tools, but if we lose track of the fundamentals from statistical learning and how this was initially designed and built, over time, these uncertainties will accumulate and it will become the norm, and we may actually head to a direction where we have more biases. I doubt that would happen. We have a lot of smart people, a lot of smart engineers out there, but it will definitely improve if it's used properly. If it's not used properly, it still can improve some predictions, but it would also, we will lose our understanding of the mechanism and the process behind it. And understanding the mechanism and process behind it is very critical when selecting your maintenance corrections. So it's not only about what is the condition next year, but why is it going there, and what do we need to do to improve that? That's also something that we should keep in mind.
Well, again, it's a pretty extensive topic. It called to mind to me that that would make a great TRB workshop or session, or at an ASCE or an industry event. I'd like to move on to the next question so we can get as many in as possible. So how different is resilient-based design compared to LRFD design with extreme loading conditions?
So again, as I mentioned at the beginning, resilience-based design, it's all about recovery. So you're looking at the functionality of the system that you have or the asset that you have. With the traditional extreme event, you're just looking at what is the maximum load and what would be the consequences if you give it a design A and you face that extreme load. Resiliency, again, it will pass that design, but the next question with resiliency-based design is, or resilience-based design is, how much does it take to recover? How much did you lose of that performance over that period of time? And what are the resources that it takes to recover from that?
Okay, let me move on to the next question here. And what resources do you recommend for learning more about practical implementation of knowledge-guided machine learning? And I'm working multiple screens here, so forgive me for a minute. Long questions.
Sure.
So go ahead. There's a twofold question, one for you and one for me. So go ahead. What recommendations do you have for learning more about knowledge-guided machine learning?
So knowledge-guided machine learning, there are less textbooks. I haven't, to be honest, seen or stumbled upon a very solid textbook on knowledge-guided. But what I have seen, there is a research group working on the performance of lakes in Minnesota, and they have done an amazing job. They have multiple publications. I've actually provided a title for one of the early papers on the topic. There are also a lot of advancements in geotechnical asset management, geotechnical engineering and knowledge-guided machine learning. I've seen one recently on piles. One of my colleagues have worked on that. There's another one on the basically predictions and the quantification of uncertainty for site investigation. So the resources are relatively, sparse, and there's no solid textbook. But if you're interested, I can provide also a list of papers as needed if you want to send me an email on that.
Okay. We've got time for one more question, and then we have to move on. And this is directed to me. And the question is, who do you anticipate will drive adoption of machine learning in the geotechnical community or industry, is the word used, the owners, consultants, and academics? And you forgot a very important component, the contractors, both general and specialty contractors. I think it's going to be somewhat of an kind of an unconscious effort that's driven by speed, is driven by cost, is driven by reliability and our need to have longevity in infrastructure to be thought about more so today, and that'll continue into the future. So it's a combination, and sometimes that'll be a collaborative combination, and sometimes it'll be independent. So with that, I'd like to have the next slide, please. And if we didn't get to your question, just please bear with us. We'll answer as many questions as we can. So I want to thank everybody for joining us today. And if you joined for the entire hour of the program, you'll receive a PDA certificate and a PDF copy of the presentation. Please allow us 3 weeks for your certificate, and about that same time, perhaps a little bit shorter, for a copy of the PDF slides that you saw today. We do not give out PowerPoint slides. That's considered intellectual property by us. So if you have any questions about our policies and procedures, you see our email address shown here. Please communicate with us. We certainly strive to make this program as beneficial as possible for everybody in the entire community, and certainly all of you who join us. So our last slide is a bit of a commercial. ARA is always looking for great people to join our team. I'm approaching very quickly my 10th year anniversary at ARA. It's in 51 years, I've only had 4 jobs. Boy, what a boring engineer I am. So we strive to hire valued colleagues that have the right skills and demonstrate our core values. And forgive me if I read this: passion, freedom, service, and growth. Now, fairly recently, probably you don't know this, ARA has got about 50 offices nationally. We just hired, not so long ago, a week or two, our 2,000th employee. We're also noted within the Bloomberg list among the top 200 defense-based contractors in the United States. Now, obviously, we do a lot more than just defense work, but that's a notable achievement on our behalf. If you're interested in employment opportunities currently within one of our 6 business sectors, that's the transportation and infrastructure sector, that's where Ahmad and I live, please send a brief resume and your contact information to www.joinara@ara.com. With that, I want to thank you all. Have a blessed day and be safe out there.